Okay, so I've already recorded this video once before, but I actually, oh, and I actually wanted to change this to just particle box. Sorry, that makes no sense if you're just watching this now. But so yeah, I recorded this whole video already once before, but I recorded probably for like an hour and 20 minutes, and that's way too much of a video, and I didn't want to edit that. It was a mess, and so I think I just want to like really break this concept that I'm going to describe to you guys. I want to break it down really simply. So first off, what is this concept? What is what I'm trying to show you? I don't know what I want to title this video, but hopefully it's you got an idea of what I'm about to show you. It's basically how to make this thing. So what was it called? Powder game. So there's this game that I used to play a long time ago, and it's this. So it's this giant this giant thing that has a bunch of pixels, and you can like put particles down, and they interact in different ways. And like if I put fire here, I can catch these things on fire, and there's some fire. I can put gunpowder, and that'll explode. C4 explodes a lot more intensely. Then there's like, let's say if I reset, if I put like water down and then I put some ice here, it should, well, I gotta, yeah, it will freeze the water. So the point is it's a bunch of pixels, and they all like interact with their neighbors and all that kind of stuff, right? And I was really fascinated with this idea. I had some ideas for this that seemed really cool that I wanted to try out, but I would have to obviously make my own because I don't know how to like edit this. And it seemed as though each particle had to like have a different way of interacting with each other particle, right? So it was a lot. This project looked like it took a long time to make. Now I don't think that's actually how it worked, but I used to think that's how it worked. I forget what Soapy does. Anyway, so the point is that there's a lot of interesting things you could do with this. So for one, let's scale it up to like 16, and we can actually do this. If we get pen 1, oh, I gotta go. Oh, I didn't go all the way up. Okay, so I want metal, and I also want the line to go away. Can I don't know if I can take the line away, but you could ooh, okay, you can make these things out of metal. You can make these like circuits in a way, or at least I thought you could, and you could put like electricity on them. So here's some electricity falling, and if they touch metal, they go through it. And that was interesting because if you had there's this other game for mobile that you could have this thing, and the electricity, when it runs through the metal, it's hot, and so when you put something that's flammable on it, it would actually catch it on fire. So you can have these interesting interactive things. Also, it's just a giant ad on the screen this whole time. You could have these interactive things, and you could set up these interesting puzzles. And I forget if am I still, yeah, I'm still zoomed up. I forget if there used to be like a, yeah, you could upload. So how do you download? Yeah, there was like you can try out people's puzzles, which I think it's like right here, or not puzzles, I should say people's projects, and then you just start it and things happen. There's some people. Now my system won't have people interacting, but and then like windmills, and there's fans, and I guess there's a whole like circuit or something. It does something. The point is you could do these all like complicated things, right? Okay, so let's go away from that. So I've built my own, and I want to talk about the interesting challenges with it, but also kind of showcase some of the interesting things that I've been doing with specifically Conway's Game of Life. So I made a video a long time ago called it was like Sierpinski's Triangle in Conway's Game of Life or something. I basically coded up Conway's Game of Life, and I'll actually demonstrate. So yeah, you can see this is the sea alive and the sea dead are Conway's like dead particles and Conway's alive particles, and they do what you expect. They interact with the world in a Conway sort of way. So the video I made a while back was about what if each particle moved up 1 at the same time it was doing its calculation. And I probably have that still. Just a recap of that. I would search probably I just put Conway, would it work? Conway, or I have no idea how to spell Sierpinski. Sierpinski's triangle. Okay, so let's just take Sierpinski and then search. Oh dear, do I not have it anymore? Okay, well, that's very strange. Triangle? Triangle. Oh wait, triangle. Triangle. Because I never wrote it down like that. Anyway, well, it just made the Sierpinski's triangle in the Conway's Game of Life. It was an interesting phenomenon thing that came about. Okay. So I thought, well, what if I change the rules a bit? And I make this one. So this is very similar. So you can see there was Conway's ones right here, the dead and the alive one. Then I made this mini one. So the way Conway's game works is that it would each particle or each cell, each pixel, would look at its 8 neighbors around it. So it would be this one, and then it would be wait, that one's gonna go away. Let's use tree. It will be these 8 surrounding it. Whereas the mini ones is different. It's this. We'll look at these. Oh crap! We'll look at these 4, like that, and you get interesting behavior. So let's actually go to the code before I even show it off. Actually, I will show it off first because that's probably better to do. So actually, I didn't need to erase that. Let's just fill the board with the dead ones, and then let's fill the board with live ones, and you get this. So this different brush sizes will get different patterns, and basically this this system, unlike Conway's Game of Life, this system likes to build squares or rectangles, and it likes to heal itself. So as you can see, it's building this rectangle, so it will eventually build over here, and there we go. And if I try to destroy it, so I get some dead ones and I cut, oh, that's a little too small. If I get some dead ones and I cut into it, not like that though, sorry, I have to, you can't make a new 2 rectangles. So if I cut into it like this, it will eventually heal and close up. And if I cut it on the corners, it'll do the same. It will eventually go. It's basically the bounds of the X axis and the Y axis, like the, you know, the bounds of the rectangle will always heal back to that bounds, if that makes sense. So I could, if I'm cutting this, there's still these pixels over to the right that are up on the top. So it's always going to go up to the top, and there's always the ones down here on the left that will be on the most left. And so it will always fill into that corner of the most top and most left or most down. And it will do it, even if it's not doing it right now. Eventually these random ones will eventually go to the random like chaos in here will eventually go to the corner. And so I think, and this one's actually taking a while, but I think, like my conjecture would be that no matter what state, no matter what like injury it takes, it will always fill up. It just has a, there we go, it's finally going up here. It always has a random chance of healing itself, but it has a 0% chance of going outside the bounds. As you can see, this really clear white line that has formed on the outside. So I think that's interesting. And I forget if there was like any other interesting things with, I didn't have to restart the page, I just realized, but if there's any other interesting things with this little mini Conway's thing, let me think. This will die. Oh no, that will, oh right. I tried to explain in the time I recorded this last time, that this thing would be able to create like circuits. I forget how I did it. Oh no, it would be this way then. Yeah, it's hard to explain, but I once did a pattern like this where it flipped direction and then it flipped the other direction, but it kept adding to it. And then if I flipped it on the same side, so if I put something here and then I put something here, it would die, it would go back in 2 instead of going out 1. And so you could have like these interesting circuits with these things. Anyway, so that's interesting, but there's a lot of like interesting things that I've created here. So these are like the path ones, and there's also the tree one, and then there's fire, and if fire touches the tree, it turns it into ash or has a random chance to turn into more fire, and so you get this like burning effect. Then there's the sand, which If you have water, water will always go above the sand, or rather sand will go under water. Same with powder, but powder turns into sand when it touches it. And so I have all these dynamic interactions, but it's really, really simple to add more. It's really simple. Oh, I also have this one. This is cool. So flow has like a, it'll flow. It'll keep like changing this pattern. And if you put it later, it like, it's hard to explain. I think you could see what's happening. It's basically has an offset that it has, and it's like trying to match the 4 neighbors offset of this sine wave, and so it like has like a flow to it, and it will, you know, flow out, and then it's averaging it. So the pixels that I created a long time ago have a really high value, like 1,000, and then I create a new one that's at 0, and so it's trying to average 0 to 1,000, which would be 500. So that's why you have these really intense like boundaries. Whereas if you start from the beginning like this, and then you just immediately go, it's not going to have that insane boundary for a while. Like I could go again, it only has one like ring, a white and black ring, and then if I wait for a while, then I'll have an even thicker ring. And if I wait for a really, really, really long time, like down here, wait in a second, and there we go, it's even thicker ring. There's like 5 in there. Anyway, so to add these things, it's really simple. I'm going to link this project in the description so you guys can use it and make your own stuff. And then I'll also explain in this video how this is made. Now I was going to make like these fancy animations for the video, but that's going to be a little tricky. I was going to like show how each particle is constructed, but instead I'll just kind of show you off to the side here. So let's grab this thing. Okay. And let's rip out everything about each thing. So let's rip out all the update function stuff. Let's rip out we have to rip out that. So let's do a new particle called I don't know. This particle is gonna try to move up and to the right. So we'll say like mover. I don't know. It's a mover, and I'm gonna just put that for the time being. Okay. So as you can see, this is a class object. Oh, great. This is a class object, but it's inherent. It's extending from particle, or like if you in C#, if you use C#, then you would say like it inherits from. It's inheriting from this other class object. So we can go to that class object, and that class object is stored in the sandbox JavaScript file, and it's right around here. Okay, so it's right here. So a particle, it has a constructor. It has a color. This is the color that's going to be shown on the screen. It has an X position, a Y position, and then a particle. These are very important. You only change these in the update function, nowhere else, because I think the thing will break, or I just haven't explored what will happen if you do it. But these particles are stored in an array, a matrix, so a 2-dimensional array. And when you change this value, on the next frame, it will try to put that particle in this new value. So let's say we put a particle, we put like a piece of ice right here. And I think that like this is a 64 by 64 matrix. So right here is probably like around 32. So it's like probably 34. And 34 by 34. It's probably like the same thing. Okay, so if I wanted to make this move to the right, I would just change x. I'd do this dot x plus equal 1. Or plus plus, right? Then the next frame, if there was no particle there, like if there was no tree there, like if this was here, it wouldn't move. It would stay where it is. But if there was only empty there, it would move it. And then this one would become an empty. And that's how it works. That's how you can use it. Now this dot particle, if you change this, so it's ice right now, and if I change this dot particle, if it was equal to new tree, because the class object is called tree, it would become a tree on the next frame. It would now become a tree like that. And so that's how you can get interactive systems working. That's how I was able to, so if I have water, the water is changing its X and Y position at random, but the Y is going down only, it's not going up. It's and then if I have something like ice, and I click ice, now it's changing this dot particle for all the waters into ice because it's touching the ice. And I'll explain how you do the touching part in a second. Okay, then there's 2 functions. These are very important for each class. If you do not create these, if you create a new class, Like the empty, this all gray stuff, this is empty. This is also an extended class, but I put it in the sandbox one because this needs to be here. So the whole system can work without this file, particles.js. The whole thing can work. It won't work without this though. So this is important. These two things, the class particle and then the empty extended particle thing, these are very important. Okay, so they need to be in here. So like, let's say I never wrote this for the empty. Should still work. Everything should be fine. If I do this, everything works fine. But in some cases, let's say empty also had a new parameter. Let's say empty had this dot power. I don't know. It had some power and it was like 80. Well, now when it clones the empty, and just bear with me here, I'll explain why the thing is cloning. There's a interesting problem that you face when you're using a computer's like going one by one in a system, and there's some like inconsistencies there, and I'll explain what I mean by that for a second. So instead I cloned the entire thing at one point, the entire array, and read from that cloned one, and I need to do that. So when you create your own clone function, you would also have to put in here, so first of all, it does let clone equals new empty, so it's creating a new empty particle. Then I set that new empty particle's color to the same color as the empty here that we had. So I don't really need to do that because I'm never actually changing the color empty. But if I did, I would have to do this. Then I would also say this dot power equals, or clone dot power equals this dot power. Okay. And that way it will, if I'm changing power ever, it will be updated by the time the calculations are made in update. And then I return clone because you have to return the clone. Okay. So let's take that off though. Oh, I left this here from last time. That's funny. Okay. When I did the last video, I put this dot power. That was an example I used, so that's why it was still there. So that shouldn't be there. Okay. Okay, save. So I lost track of what I was about to say. Oh, okay. So we're making mover. So what we do is, I don't want lerp here. I don't want that to color. Let's say the color initially is, I don't know, some like, we'll make it yellow. So 255. I can't see my keyboard. Okay, so that's the RGB for yellow. And now if we just go into menu, and this is a system I've created to have these menus over here. And in the function particle menu, which is called in the beginning of Sketch, somewhere around here, right here. It creates all these buttons. So this is a chaos, but I'll show you what it really is. If I just move this over, this is what it is. Let's format that. Okay, and let's go back down. So if I copy this thing, and as you can see, this is one line, right? This is like one line, even though it's like split up into multiple lines. This is one thing. So you just copy this thing, you paste it. So you say menu.add button. So you're adding a button to the screen. You can name it something, some text. So we're saying mover. We'll have a base color, and we could just do the 255 so it'll be yellow. So we know that it's going to be that color of the particle. Since it's a bright color, we'll make it dark. So the text. Oh, sorry. This is the color of the button, and this is the color of the text. Since the button color is bright, we'll make the text color dark so we can read it. Then this is just a bunch of math to get it to the screen. If you wanted it to be on that right panel, this would be the first column. If it's 0, it'll be the first column of the panel. So when it's 0, it's on this column right here. And when that value is a 1, which I lost the value. Are we all the way down? Wait, what did I do? Where did I paste did I delete something? Oh, that was weird. I couldn't go down any farther. Anyway, so, and if it's a 1, it goes onto the right path. And then this times area. So all the things next to the multiplication. This 8 will go on the 8th rank. So 1, 2, 3, 4, 5, 6, 7, 8. So it would overlap many alive. So we don't want that. Actually, no, it wouldn't overlap. It would be, this is 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8. It'll be right here. If I put this to 1. And then I'll make this mover. So in the function on selected particle type, you just set it to the class mover. So when I click this button, it'll select that mover type, and then it'll use that to create the object. So there we go. Now we have a bunch of particles that are yellow and they do nothing. Now if we go over here and in update, all I'm going to do is say this dot x plus plus. So at this point now they will move to the right when I create them, and they kind of like, you know, open up a little bit, like those gaps in between, because as I said before, like let's say we have a piece of ice, right? And then we have two pieces of ice. If they both want to move right, this piece of ice that my mouse is over can't move into this one, so it stays. But this one can because it's empty. So then you'll get the next frame, it will look like this. And then the next frame, it will look like this. And it will follow this pattern always. It'll be one separated until it lands. So that's why that does that. Okay, and then we could do this dot y plus plus. So now it's moving up and to the right. All right, and so that's the effect. That kind of looks cool, actually. Like the tail. Okay, and then instead of that, we could actually do something like this. Well, this dot x plus equals, and I think I could do a random value here of, even though it's yeah, a -1 and 1, I think it would be fine to do a random value, because I think if it gets like 0.3, how do you move 0.3 particles in a direction? You can't. So instead, I round it. So I think this should be fine, and this should be fine. And now it's rounded and it'll just go crazy. Yeah, so this is kind of how I do the gas. Oh wait, do I have gas here? Oh, I don't have gas on this one. This is like how I do fire, except fire goes straight up. So it has a random X and Y, but it doesn't have a random, sorry, it has a random X left and right, but not up and down. It just goes straight up. So you got some like mover gas stuff. Okay, so now that's cool. You can move the thing, and then I could actually do something like this. These are like, what I'm basically showing you is the basic things on how to make like really simple particles interact. So this dot color, and what I'll do is I'll say this dot color equals a color, and I'll say random 255. So it'll be a random gray scaled color. So it'll start yellow, but it will turn into a random grayscale. So actually, if I stop it from moving, this is what it would look like. That's what it's doing. So you get how you could change the color. And so one thing I should mention that's very important is this thing right here, sandbox. The update function receives the sandbox. The sandbox is this whole box of particles. It's everything to do with the particles. In sandbox, there's a few functions you can call, or you can use the predetermined one or the pre-created ones that I've made. So over in sandbox tools, see sandbox tools right here. There's a few functions. There's the get for is touching for neighbors 4, and then there's the get 8 is touching 8 and 4 neighbors 8. What this does is for the get for, it will return the 4 neighboring pixels to each for the pixel you choose. So if you're at 3, 3 on the board, if you're at the index 3, 3 on the board, or like rather if you're, as I did it before, if you're here, whoops, if you're here and you use the get for on this location, it's going to return to you the pixel here, 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 and here. But it won't return that pixel, it will return a complete copy of that pixel. Because if you return that pixel and made changes to that pixel, then by the time you get to that pixel, it would have been different. But you want everything to happen in parallel. You don't want things to happen, you know, one moment towards the other. So, okay, before I explain this and what I was just talking about here, I'll explain with paint. So this is the demo I did in the last video, and I mean the last video I tried recording. Let's say we have a black square and a red square, okay? And what the black square's rule is if it's touching a red square, the next frame it will turn red, and then for the red square, if it's touching a black square, it will turn black. So after one iteration, we expect this to happen. This is what we should see. And then after that next iteration, it will go back to this. And it will flip back from this. And it will just be like flip, flop, flip, flop. And I could actually demonstrate, well, that would take us time to demonstrate that, so never mind. So instead, what we get is not that. So let's do this again. What will happen is if we do not clone the whole array of particles, this black one will look at its neighbors and we'll see, oh, it's red, so let me turn red. Boom, it turned red. Then we go to the red one next to it and we say, okay, is there any black ones around it? Is there? Well, there's not. So this is the outcome of that situation. Clearly, red and red is not what we were looking for. So instead, the way we get around that is we do this. Right when we do the update, we copy, we clone. Okay. And now this pixel, let's get a distinguishing, this pixel right here is going to look at this pixel's neighbors. Okay. And this one will look at this pixel's neighbors. So that when this one sees that this one has a red neighbor, this one turns red. This one's going to turn red. And then this one will look at this one and see, oh, it's a black one next to it. So let me turn black. And you get the point. So that's how we do it. So we have to clone. Every time we update, we have to clone the particles. And that's why there's a clone function. Okay, so back to this thing. As we say, the get4 gets the 4 neighbors surrounding it. The isTouching goes over each 4 neighbors. So you give it neighbors. Actually, sorry, I should go back to the get4. You give it the sandbox in get4. So if we go back to the particles and I want to create neighbors, I want to get the neighbors. So I'll say let neighbors equals get4. And then I'm going to give it sandbox. And then I'm going to say, okay, we're at this X and this Y. Okay. So now it's going to get the 4 neighbors. For all the movers on the screen, right now it is getting its neighbors. Okay. And then what we could do is say, okay, well, there's a bunch of things in neighbors, right? Let's go to neighbors. When it returns, so this is the code for neighbors. You don't have to worry about any of this stuff. This is just clamping the value so that if you have a particle on the corner and you say get the one to the left of it, it won't mess up. It'll just get the same. It will get the one that's at the most left, because clearly there's nothing to the left of this. It's undefined. So you don't want that. So it just clamps it, and then it returns these values. So it returns an up position. So if you want to get the particle's position that's 1 above the particle, obviously it would be this dot y plus 1. But if you didn't want to use that, you could use the up position. Oh, sorry. It wouldn't just be this dot y plus 1. This is important because if you're at the top, let me make this brush smaller. If you're up here and you look 1 up, there's nothing there, and so this dot y plus 1 would be bad, but up position dot y is good because it would clamp back down to this part. And then, so that's the same for down pause, left pause, right pause. The clamp up, clamp left, clamp down, and clamp right just tells you if it did clamp, if it was on an edge, because you don't know if this particle was on an edge or not, unless you want to do the code yourself. So we just say, okay, if you looked at a particle to the left and you wanted to make sure, like, let's say when fire hits the roof, it doesn't do this, but if fire hit the roof and it looked up and there's nothing there, it should just die, just like it would. Well, it doesn't, but you get the point. Okay, sorry. The main things is right here. Up, down, left, and right. This is looking at sandbox, so you just gave it sandbox. Then there's safe box. This is the cloned box of all the particles. What you're seeing right on the screen is box, but then there's safe box as well. So there's 2 things. Box is the one what you're seeing on the screen, and safe box is the cloned version of this, where you can read from without any problem. You could read from safe box, you can write to box. And then these are the positions. Okay, so now that we know what that gets you, okay, let's go to particles. So now this is getting all the neighbors, and let's say that neighbors dot up. So we're looking at the up particle, and we say if sorry, I'm doing this backwards in a way. So if that particle is an instance of mover. So if above is a mover, so for a lot of these particles in here, it would satisfy this condition. If it's a mover, then we say this dot y minus minus. So if there's a mover above, we go down. And now I believe it should do that. Yeah, it pushes it down. We can even do something like we could do more. Sorry, I had a brain fart there. Let's do this, and then, whoops. So instead of that, we do down, and we do plus plus, we do left, and we do x plus plus, and then we do right, which is minus minus for the x. So if there is a particle on the right that's a mover, it's going to move left, and so on and so forth. So they all move away from each other. And there we go. And that's pretty cool, actually. So if I actually like this a lot. This is so cool. I haven't made one like this before. They just kind of push each other away. Or rather, they don't want to be next to each other. Now, this is okay. So clearly, we see that there could be these kind of diagonal ones. And let's say we didn't want that. Then we could use get 8. It'll now get the 8 surrounding. And we'll add 4 more conditions. And we'll say there is also now there's up left. There's up right. There's down left. And then there's down right. Okay, and now we have to kind of combine these x changes. So up left is going to mean, so if there's one up and to the left, we have to move down and to the right. So x, well, actually I want to do x on top and then plus plus. And let's just copy this for all of these. Whoops. Now after this is done, they all should be like they should all look like this area, except not offset in this weird way. So up left, so then this would be up right would be minus minus. Down left, if it's down left, it's up right. Up right. And then this one, down right, would be up left. This one changes both of these. Okay, and now they will, whoa, that's a little bit different than I was expecting. Well, they're not diagonal, but now they still can be offset in weird ways. I guess that does make sense. They wouldn't be like, yeah, they can have 2 away. Because you could have this at a starting position. Oh, that's cool. It didn't create a new one, by the way. I just held the mouse button too long. So yeah, they just move away from each other now. Oh, and they move away in 2s, right? Because they're both moving away. That makes sense. So this would be fine. This is cool though. I like this, like this thing. If I put something in there. Now if you have too many, obviously they'll always try to keep moving. And they won't ever stop. Anyway, okay, so that's how you use the neighbors. Now, what I just did is I said if each specific one is of instance of, right? Let's say there's a situation like you have with water and ice. With water, it doesn't matter what direction ice is in. If it's just touching ice, it should freeze, right? It doesn't matter. So if we go up to the water function, which is all the way at the top, somewhere, right here, we can see that we're doing here is, we say, we could use this function, the is touching 4. We say if is touching 4, we give it the neighbors. And so now it's going to run through all the neighbors, and then we're going to use this function to check something. So we give it a non-named function. The function is receiving a particle. I don't know why I named n here. It'd just be like particle. And we return true or we return the statement particle instance of ice. So we're saying if it's an ice particle, then return true. If it's not particle, then return false. And this is a nice function because the second it finds a ice particle, it stops calculating. So it's efficient. It is as efficient as it could be. Then the second it returns true, it says, okay, we're gonna let limit equal this dot freeze up, and I'll explain what this is. I have these particle modules. I only have one in here, but it's a limiter, and the limiter just has a value. It has an uptick. So let's say for ice, obviously you saw that the water did not turn into ice instantly, right? It slowly went across. That is because it starts at a value of 0 of freeze. It goes up by 1 of freeze, and the second it gets to 3 of freeze, it freezes, which is the limit up. Then there's also down and limit down, but we're not going down and freeze. We're not using that, but you could use that. Okay. There's actually so much to talk about here. I'm just kind of, yeah, there's just so much. Okay, so I'm not going to go through all of it. I'm already at 34 minutes. So I would like to wrap this up. Well, not yet, but soon. So, and then, okay, so important thing is when you're ever changing the particle, so obviously when limit is true, this dot particle equals a new ice, return. Make sure you return, because if you don't, I mean, you don't have to, but like, if I create a new particle, then anything after, if I set this particle to a new particle, anything after won't take effect. Even though it'll do the calculations, it doesn't matter because that particle disappears. Because the next frame is this new particle, and new ice does not have any code that's making it do this. So I just return here, and it stops from less calculations. Okay, so let's go back to mover. I want to try one more thing. I want to interact with something. So obviously we're just doing mover, or rather we're just looking for mover. Actually, yeah. So what we'll do is this. We'll say we'll let touching equals 0, and we'll do this dot, oh, not this dot touching, we'll do touching plus plus. Okay, and now if it's ever touching a particle, it's gonna do touching plus plus. There we go, there we go. And the reason I'm doing this is because I want to change the color based on how many particles it's actually touching. So then what we'll do is we'll do this dot color equals color, and we're gonna do, we want it to be yellow, right? So we'll say it'll get more red. Yeah, it'll get more red if it's touching more things. So we're gonna have the 255 there anyway for the red channel, but we're gonna map the touching from 0 particles to 8 particles is touching, to be from, so 0, if it's not touching anything, it's 255, it's yellow, and then 0. If that didn't make sense, I am sorry. Okay, so now it will be more red the more it's touching. Yeah, there we go. So you can see that the inside is more red. So yeah, I mean, this is very interesting to me. It may be interesting to you. I know there's a ton of people that would not care at all about this, but I think if you're watching this video, then you probably do care about this, and it's just fun to mess around with, and you can make some really like complex things with it. So that's also really fun too, if you can work your head around that. Now I'm not that good with that kind of stuff, but I want to be, so that's why I've created my own system. Now I will say, if I'm using JavaScript here, and I'm using the P5 website. P5 website is website. Here's a link to my thing. I'll just link it in the description. But this website is for kind of doing this stuff to be able to code, but also visualize it in a way that's aesthetic. If I wonder what happens if I do this. If I go to the create canvas, you don't even know what I'm doing here, but WebGL. Will this still do stuff? Okay, so it did switch over. It did push that over to the side. But I believe now, if I were to, if I were to do this, rotate X by frame count. Oh, times 0.01. I don't want it to go freaking crazy. Okay, it's not doing it, and that's probably because rect doesn't create. It should. Is it not X? Is it Y? Okay, sorry. It's in 3D now, by the way. So if I do something like box 0. Oh wait, no. Yeah, 0, 0, and then. Oh no, you don't do that. You just do box 50. We'll do 500. Yeah, that's way bigger than I thought. 50. You can see it though. So yeah, you can make 3D things. So sorry, what I was basically saying is that you could do this whole program, this whole system, but with cubes instead. You could do it with cubes. You could have a 3D thing doing this whole thing. I just did it in 2D. So if you want to have that as inspiration, there you go. Okay, the last thing I want to do is I want to explain how the sandbox calculates its sandbox stuff, because that's very important. Now, you could go to the code and look at it and try to figure it out yourself, but I know that's going to be kind of difficult, especially if you don't know how I code normally, and I don't make comments good enough to really understand the code. So you would have to kind of like run the code in your brain to understand what I'm doing. But basically, in Sketch, this is the main thing. This is what runs the whole program. I basically create a sandbox. I create a selected particle types. This is what you're going to draw with. And then I create a menu, and then I create a brush size, which actually the brush size doesn't matter anymore because I've moved that into the sandbox. Oh, it does matter. I'm being dumb. It does matter. Okay, so in the draw loop, so this is for P5, if you don't know, this draw loop right here, this is what runs every frame. And I have the frame rate at 200. It doesn't get to 200 because it's moving. There's too many calculations. But if I had this at like 2020, that's funny. That was last year. Then it moves a lot faster, as you can see. So, oh yeah, I forgot to mention that glass is also pretty cool. There's some glass behind here, and that's what happens when you heat up sand. It turns into glass. Anyway, I'm getting distracted. So clearly you can see how fast the particles move. It's not just because they're closer. They are actually being calculated a lot faster. If I do 128 by 128, let's say, and I do the fire, see how slow it is? And now I'm in JavaScript, right? And you would probably think, oh, let me do this in C# or Python or something. But I don't know if you can really. I mean, you probably could, but I don't know how to do it. And it's because you need to make an array of, if you want to do it in the way I'm doing it here, you need to make an array of particles where each item in each, sorry, not an array, a matrix. You need to make a matrix of particles, and each item in the array, the matrix, oh my god, I'm stumbling on my own words. Each item in the matrix has to be a different type. It has to be a different class. Like all of these are fire particles and are fire type, and the other ones are empty type. And you need to be able to store them together. C# you can't do that. You have to have a list of all the same item. So yeah. Anyway, in the draw loop, what we do is we render the particles to the screen, and then we update. Now I have update happening after render. Usually you would have it before, but I have it after because originally I had it where it would like do this. I would have sandbox dot place, and then I would have at 20, 50, and I would say a new ice, and then boom, it places one. But I wanted to see it there before any effects happen, because let's say, you know, obviously if I placed it here and I place water next to it, let's say, let's do 1, and I did water, it would, and let's pretend that it instantly turned into ice, you wouldn't see ice and water on the first frame. You would see ice and ice on the first frame because it updated before it rendered. But anyways, that's why I did that. So in the update function, what it does is it resets movement parameters. So let's see what that is. Oh, right. So it goes to box. So this is what you're seeing on the screen right now is box. So this dot box, and it goes to each particle, and it just gives them their position, their X and Y. And then it also gives the particle itself. So particle is set to itself. So the next frame, it will become itself. That's how you can have these things exist, but also become something different. Because the next frame, if particle is changed, it will become something different. Like if I put fire here, it will become ash or fire. But it would also become itself if you don't change it. Then we create a list of movements. So this is where all the particles are trying to go to. This is also what they're trying to become. So we just create an array, or sorry, not a list. We create a matrix. So for X, so the width of the system and the height of the system. Okay. Then I clone everything. So this dot safe box equals a new matrix, and then in safe box, I'm just going to the particle and cloning it. So if you don't write that clone function, this is the moment where it uses the previous clone function from the base class particle, and it won't, you know, do what you expected. The next thing I'm doing is, and sorry if I'm jumping over these fast. I feel like if you don't understand what's going on with the syntax here, then maybe it's a little too advanced for you right now. But basically, I'm just looping over things over and over again. So for X, I'm looping over all the X locations, and then for every X location, I'm looping over all the Y locations. And then I'm just doing something for each. And then at this moment, I'm also creating the safe box as I'm filling the safe box in. Okay, so this one's record all particles movements to movement array. So I'm guessing, yeah. So this calls box.particle to update. It gives it the sandbox. This is the same thing. This right here, this line is this update sandbox. So okay, and then after it's updated, so this is the moment where it would probably do like this.x has increased by 1. It's moved over 1, and then it creates a variable. So new x and new y location is the clamped version of that x. So if it moved over left, but it's on the corner of the wall, it clamps it so it doesn't move over. So the new x location is its same position, so that if it wants to go left, it can't. So that's how you keep it from going out of the bounds and breaking the system. Then we set and then we put that back into itself. So we clamped the new this.x and then we put it back into itself. Then we do let new particle equals, I actually didn't need to make a variable here. I could just put this whole thing like in there, but I'm not going to do that. I'll leave it here. And what this is doing is it's in movements. It's going to that new position and it's pushing it in the new particle. So in other words, if I should draw this so it makes sense. And now I'm actually going over 45 minutes, which I kind of want to cap it there, but I guess I can't. So what we typically have is a matrix. So we have these particles. Let's say this is a 3x3 matrix. Oops. And that is what the box has. But movement is actually a 3-dimensional matrix. Not only does it have each location, x and y, but for each thing it has, another depth, another list of particles, right? I can keep doing this, but I'll just stop here. You get the point. And actually, it's a good representation. Do something like this. Some will have more particles than the others. Some might even completely not have anything in that spot, right? Because let's say this particle moved up and to the right, and then this particle moved to the right, and this one moved up. And so now this spot is filling up with particles. And so what I do is after we have this like list of items in there, I'm not going to save that, which is right here. Okay, well, before we do that, we then just create a new sandbox. This is going to be the new box, new sandbox, new box. Then down here is the magic. This is what makes sure that nothing overlaps, nothing takes its place, and nothing like gets destroyed. So if you ever try to create this on your own, when you try to have the particles move around, there's a really high chance that 2 particles will move into the same spot, and then one dies, one gets destroyed, and that's not good. So we get the new x location, new y location of each particle. Then what we're doing is and this is kind of complicated to say, but we're checking to make sure that the position that we're at right now, when we're looping over all the particles, the position that we're at right now is sorry, I just wanted to burn that, is empty. So if we're at an empty square right now, then we don't care about it. And that goes down to here. And we say, okay, if we don't care about that particle, we still have to make sure that if that empty is trying to become a particle, then we do set it to a particle. So this empty, right? Let's say, like for path start is these path things that go out and everything. What I'm doing is when a path is created, so let's pretend this ice is the path start, the purple one. This one, it picks a random direction and it's like, okay, I want to go left, but it doesn't make the left yet. It checks the surrounding neighbors for any path objects or path particles. If there is no path particle, it then sets itself there. And that's why you can see like these gaps and and yeah, so I was trying to make like a maze particle. It didn't really work out that way. They kind of just are too random and chaotic, and they have these like corners touching, which I didn't want. I wanted everything to be like perfectly open, like kind of like this or something. Anyway, it didn't work out that way, but you get the point. They're basically changing the empty particle. We're changing the empty particle into a path particle every time the path moves. And so if we ignore the empties, then we never do this part. So when we do ignore the empties, if the particle is not an empty itself, then we just set the particle to a new particle. Okay, that was chaotic, and I don't know if you understood any of that. This is a very important part, but honestly, if you don't understand it, you could just copy this. You could just copy the whole code. It's open source. I don't really care. This is just really fun, and I've always wanted to make something like this, and I've never found anything online that is like open source like this. So I just decided to make my own. Finally, I've been trying to do this for years, literally years, and now I've done it. So after we determine that it is not an empty, right? It's one of these particles. Then we say, okay, this particle, if this particle is trying to go to, let's say this ice particle is trying to go up and to the left, we check up and to the left. Pretend this ice isn't there, so let's delete that. We say, oh, I didn't mean to do that. So up and to the left, we check, is that empty? If that's empty, then we can just move the ice there, because nothing else was trying to go to that spot. But what if this ice over here was trying to go down into the left? They were both trying to go to that same spot on the board. If they're both trying to go to that same spot on the board, then they both don't go to that spot because it's not empty. The movements is what's holding the fact that it went there. So move in the movements array, both particles exist in there. It's that thing I just did in Paint. And so yeah. And then after we determine that it can make a change, it can move somewhere, then we just set that particle, that new particle's location to the particle's particle. the particle we're looking at's new particle, meaning this thing. This thing. This dot particle equals new fire, right? This is for glob. Oh yeah, so glob is funny. I was trying to work with glob. I was trying to make something that like acts like water sticking to each other, but it didn't really work out. It just kind of breaks apart and like falls. But then it's kind of interesting. It makes these weird bouncy things, and I wanted to have it set on fire, and that's what it does. Anyway, okay. So then after it does that, so it's checking all the legal moves. And then the last step to do is to fill in all the gaps in the new sandbox that didn't get anything. Because if you think about it, let's say this ice particle, okay, not that. Let's go down. This ice particle, let's say this one's trying to go up, but nothing was trying to go towards the center. So everything went away from that center, meaning there's nothing there even in the new particle, or new sandbox. Not even empty. There's literally nothing in that spot. It's null. So we say if it's null, then just create a new empty. So new empty is the only particle that gets created out of nowhere, besides you creating the particles by clicking on these and creating them. Everything else does not go away unless you've coded it to go away, right? Sorry, I was getting interested in this. What is happening? Oh, look at that. It's like trying to push away. It's about to end, I think. Kind of looks like it's creating. Okay. I thought it was creating new particles on its own. Sorry, I get really distracted. Okay, and the last thing I should mention is this function. Now, you don't really need to... Oh, actually, it won't be the last thing. This will be the last thing. The set, place, and influence, and safe get. Actually, you don't even need to know what this is. This is just checking if each location doesn't have the empty, or if it's not itself particle. Yeah, that's a complicated mess. That's very important though, but it's not you just need it there, and you need to use it in the right spot. You don't need to know what it does. It's like the magic black box thing. Okay, last thing. This is literally about to be an hour-long video. At least I didn't have to cut this time. Last time I made so many cuts. So we have the set function, we have the place function, the influence function, and the safe get function. Basically, that whole thing that I had earlier, where you got the 4 neighbors around or the 8 neighbors around, it essentially used the safe get function, except it didn't. It used the code in here, but not the actual function, because I made the code first before I made this function. But I thought, well, what if you had a particle that didn't want to look at its neighbors? What if you wanted a particle that looked 5 up above it, or 20 above it, or a specific location around it that wasn't its neighbors? And that's what glob does, actually. Glob looks at I think 2 over. Let's see. Glob is like lower down. This is glob. Yeah, it looks 2 over, so it's not looking at its neighbor. It looks it's the neighbor's neighbor. And that's how the functionality works. That's how it like moves, but then it gets sticky to itself, but then it like falls apart, and like it'll drip. It's like dripping on itself. Okay, and let me close that up. Sorry, like my OCD here. Okay, so that's what SafeGet does. Is basically you give it a position on the board. If that position is out of bounds, it gets clamped, and then you get the particle from SafeBox, specifically SafeBox, because remember, you're reading the cloned version. You don't want to read the version because it might be different from after you make an update, and then you return it. Now the 3 others are changing, so this is getting information. The other ones are setting information. So set so if you want to use set, it just changes the particle at box, on the box. So if you're using set in the update function of a particle, that's kind of bad, because then you're is it bad? Wait, actually it is bad. It is bad, because then the next particle will run its update, but it will run its update not as the particle it was, but as the new particle you set it to, and that's lopsided. That will cause problems, and I'm explaining that wrong, but just trust me. It's hard to explain, but yeah. But set is really good for when you're placing things down on the screen. That's what I use here. So I use set and place. So place and set do the same thing, but place only sets things if that particle isn't empty. So if I have like tree, I have a bunch of tree, and then I create ice. If I click down, it's not going to do anything until I get over here, so it doesn't overlap. So that's what place is doing. And then set is like, if I have this, I'm like overlapping, because I wanted these guys to overlap each other, and so it kind of just overlaps everything. And that's because beforehand, if you wanted to do a Conway's game and you were filling this in and you wanted to create a specific configuration, you would have to then go in, delete the shape, go back, and then fill it in like that. Oh, well, it would have filled it in without overlapping. Now you can just go in and you can actually just place your things that you want. And then you could also go in and say that maybe if you're holding down F, the thing stops calculating. Like, so you can like freeze time, put your objects in, and then unfreeze time. Okay, so, and then influence. Influence is important, because influence is like, okay, well, if you have a piece of ice, and that ice is supposed to be influencing. Actually, I could do this right now. So let's go to particles, and let's find ice. There's ice. Okay, and we'll go into update function, and what we'll do is we'll do sandbox dot influence, and then we'll say this dot x plus, no, that's not what I mean. This x plus 1, this dot y plus 0, and then we're going to influence it. We're going to try to make that particle an ice. Okay, so if I run this now, you'll just see that it's going to do that. So what it's doing is each ice particle is telling its neighbor that in the next frame, become ice. Not this frame, but the next frame. And that's how you can get these kind of things. So we can say this too. We can say let right equal, actually we don't even need to do let right equal that. We have the right already. We have neighbors. So we say if neighbors dot right is an instance instance of ice. So we say if it's an instance of ice, we don't do this. We don't try to change it, because you see how the ice is like getting changed constantly. You see how it's like flickering. Now watch what happens. It won't flick. Oh, wait. Sorry, I did it backwards, I think. Oh yeah. If it's not that, now we're just updating it only if it is ice. So if it is not a piece of ice, gosh, sorry, it's hard to see my keyboard when I have the mic in front of my face. Oh, yeah, hold on, there we go. Okay, if it's not ice, then it'll go out. Now that's a little nicer. And we could just do something like this, where we do right, we do left, we do up, we do down, then we do, I can't see my keyboard, we do negative, and then we do 0, 0, we do 1, negative 1. And now should just kind of go out. There we go. We fill a gap. So it's a good way to fill gaps. So like if we had something like glass, we should draw some glass around. Oh, that's not drawing actually. I just realized, because it was probably doing something like that. It was probably leaving gaps. Let's well, we could still use the dead. So let's draw like, oh, I didn't mean to make it that small. Let's draw this. I don't know what shape I'm making. I was gonna fill this area, but then I just turned it, and then we just do that. And oh, right, sorry. Let's actually instead then what we'll do is not this. We'll say only if it's empty. So we delete all this. We don't need that not gate anymore. We say only if it's an instance of empty, which actually is better, because then we'll just use tree or something. I don't know. We do this, and then when we do ice, it fills in the gap. It's like a paint bucket, except it takes a while to do it. So there we go. That is the thing of the things. And I think that's about it. I went over an hour, but yeah, yeah. So I'm gonna link everything in the description. I hope you liked it. I hope this is inspiring, and I would love to see someone take this and go all out with it. Like make something that has a ton of these particles, or even the system could even do something like this, where you can have a particle that its properties are defined by other parameters. So what I mean by this is, let's say we go into the particles, and we are in particles, and let's say in ice, right? Let's say ice, or let's say we had a particle that had a density and a mass and a electromagnetism field thing, blah blah, and then those parameters define how it interacts with all the other particles around it, and so they like bounce and move at each other and stuff like that. And based on those things, you can create systems like do I still have this? Hold on, let me see if I still have a project that I worked a while back on. What would I call it? I don't think I called it particle. Did I? Particle automata. It's particle life. Is it particle life? It is particle life. Okay. Oh, it's really laggy, but yeah. So this was really cool. It's really zoomed out. So let me zoom it back in. Where is zoom in? How did I zoom it out? Oh, scale. Oh, so FOV. Let me turn the FOV 1 over FOV. So the smaller it is, it's gonna be closer. Yeah. So what this is these particles all have a tag. They're all a certain type, and they interact with each other the same way if they're the same type of particle. But I can press the numbers and they interact differently. They have different movements. So like, see, purple and orange don't interact with each other at all, or at least orange does not get affected by purple at all. And what this allows is for, if I do a bunch, you can have these cells. They interact in a way where they create like movers, and they'll position themselves in a specific orientation. And I can show this better. Oh, over here in processing. Let's see, this is off screen right now, just have fun looking at my background or my desktop. So processing, then scripts, then P5, then oh, maybe not P5. Did I make it in Java? Atoms, particle systems. Yeah, this is, you're just looking at nothing. How about this while I'm searching? Because I don't want to cut. While I'm searching, let's create a fun system of things that do stuff, and then movers. There we go. Is it particle system? It's opening. I made it in processing as well because it could run faster. Yeah. Oh, so it's not that, but that's a very interesting thing that popped up that you can't see. Well, you get the point. There was some really cool stuff that emerged, some of these really cool properties that emerged from those systems where like it almost looked like there was life. They would move and interact in these bizarre ways. And oh, I can find it. I just realized I think I know how to find it. Or rather, I don't know how to find it, but I did create an animation of it, and I just saw the animation folder. So okay, and it's completely gone. Completely. All right, well, you're just gonna take my word for it. But yeah, you could probably do that in this thing. You could probably have systems where they interact with each other based on properties rather than based on what type they are, which would be really cool. So you don't even need a bunch of list of particles. You could just have one type, the atom particle, and they interact based on their amount of protons and electrons and neutrons they have inside the class object, which would be like right here. So yeah, so there you go. I hope you enjoyed that and hope you liked this video. If you stuck this long in the video, that is insane. I feel like that is so rare, but thank you so much. That means so much to me. And I definitely hope that you guys comment. Definitely comment. And if you want to like, you can like and subscribe. Yeah, the whole yeah, I was gonna do the whole I have, you know, or 99.999% of you guys don't subscribe to my channel, but it's actually true from my situation because a lot of my videos went kind of crazy with the views, but I barely just hit 90 subscribers, which is still insane to me. Imagine 90 people in a room. Anyway, I hope you enjoyed, and thank you for watching.